Welcome back, everyone, to the deep dive. Today, we're going to try to tackle something, pretty crucial when it comes to AI. We're always hearing about these amazing predictions AI can make, but how do we actually know why it's making those predictions?
Yeah, that's the million-dollar question, isn't it? I mean,
Yeah.
knowing what an AI predicts, that's great. But understanding the why behind it, that's where the real power is, right? We can build better systems, we can spot potential issues, we can really get the most out of AI, and that's what we're digging into today.
Right.
We're talking about explainable AI, XAI for short, and specifically, we'll focus on three big techniques that help us, uh, you know, kind of peek under the hood. Feature importance, partial dependence plots, and subpopulation analysis.
Okay, so think of this as like your crash course in XAI essentials. We're going to try to give you, the listener, a solid grasp of these tools, how they work, why they matter in the real world. It's not just about knowing the terms, it's about understanding their practical power.
Yeah. Exactly. But it's important to be realistic too, right? These XAI tools, they're super helpful, no doubt, but they're not magic bullets. Uh, they work best when they're used carefully, interpreted thoughtfully. If you misuse them, well, you can end up with the wrong conclusions. You can even make existing problems in your data worse. A classic example is, well, many feature importance methods assume that the different pieces of information you're feeding into the AI are like totally independent of each other. And in the real world, that's often not the case.
Yeah, totally. And it's not just about whether the data points are like totally separate. Even the way you combine those individual insights, to figure out which features matter most overall, that can make a huge difference. Like using different ways to kind of summarize or aggregate the data can lead to different rankings, different conclusions. So a bit of caution, a solid understanding of the basics, that's definitely key here.
No doubt about it. So, before we get into the specifics, maybe let's just quickly define these three core ideas, feature importance, partial dependence plots, subpopulation analysis. Think of them as different lenses we can use to examine how an AI model makes its decisions.
Okay, sounds good. Let's start with feature importance. Like, in simple terms, what is it telling us? And why should the listener actually care?
Right. So feature importance is all about figuring out which of the inputs, the variables you're feeding into the AI, are having the biggest impact on its predictions. Basically, it ranks those input features by how much they contribute to the final output.
Okay, so like if you were trying to predict something like, I don't know, the price of a house, you'd have all these features, right? Square footage, number of bedrooms, the zip code, year it was built, all that stuff. Feature importance would tell you which of those factors are the real drivers of the AI's predicted price. So maybe square footage and location are the heavy hitters, while the exact year it was built has a much smaller effect.
Yeah, exactly. And there are a bunch of different ways to measure this importance. We can kind of group them into two main categories: model-specific and model-agnostic. Model-specific means the technique is tied to a particular type of AI model, while model-agnostic means it can be used on pretty much any model.
Okay, got it. Let's dive into the model specific ones first. What makes them unique?
Sure. So with model-specific techniques, you're really looking at the internal mechanics of that specific type of AI to understand how features are influencing things. For example, if you have a simple linear regression model, the size of the coefficient day, that number attached to each feature in the equation tells you how important it is. A big positive or negative number means that feature has a strong pull on the prediction.
So, like, imagine an AI trying to figure out if someone's going to default on a loan. If the credit score feature has a huge negative coefficient, that means a higher credit score dramatically lowers the chance of default, right?
Exactly. Now, with more complex models, like tree-based models, things like decision trees or random forests, feature importance is often measured by how often a particular feature is used to split the data into different groups and how effectively it does that. They use these metrics like Jaden impurity or information gain. Think of those as ways to measure how much each split improves the model's accuracy. If a feature consistently leads to big improvements in accuracy when it's used to divide the data, well, that's a sign it's an important feature.
So, if you're trying to predict which customers are going to cancel their service, and the AI keeps using the contract type feature right at the beginning to separate customers who stay from those who leave, that means contract type is a pretty crucial predictor, right? Like the AI is basically saying, this is the most important thing to know when making this decision.
Yeah, that's a great way to put it. Now let's switch gears to model agnostic tools. These are cool because they don't care about the inner workings of the AI. They treat it like a black box and try to figure out which features matter by seeing how the model's predictions change when you mess with the input features.
Okay, that's interesting. So, how do you actually do that? Can you give us a concrete example?
Sure. One of the most popular model agnostic techniques is called permutation feature importance, or PFI. It's a pretty simple idea.
Mm.
You take one feature of your data set and you randomly shuffle all its values. You keep everything else the same, just mix up that one feature. Then you feed this modified data back into the AI and see what happens to its performance.
So, if the model's accuracy takes a nosedive after you've scrambled the values of a particular feature, that means that feature was really important for making good predictions in the first place, right? Because by messing it up, you've taken away some crucial information that the AI was relying on.
Exactly. The bigger the drop in performance, the more important that feature was. It's like the AI is suddenly lost without that specific piece of information.
Okay, so let's say you've got an AI that's supposed to spot fraudulent transactions. If you randomly mix up all the transaction values and the AI suddenly gets way worse at flagging fraud, well, that tells you that the transaction amount is probably a key indicator of fraudulent activity.
Precisely. Now, there are a few important things to remember when you're working with feature importance. First off, look for consistency in your results. If you train the same AI multiple times, or if you train slightly different models on the same data, and the rankings of feature importance are all over the place, that's a red flag. You might not be getting a reliable picture and you need to investigate further.
Yeah, that makes sense. You want to see a clear, stable pattern in terms of which features the AI thinks are important. What else should we watch out for?
Another big one is the problem of correlated features. Features that are basically telling the AI the same thing, like income and debt-to-income ratio. Those two are obviously related. Because they share so much information, their individual importance scores might not tell the whole story. The importance might get spread between them in a way that doesn't accurately reflect their combined influence.
So if you've got two features that are like two sides of the same coin, their individual importance might seem lower than it actually is if you looked at their combined impact, right?
Right. And techniques like variance inflation factor, or VIF, can help you detect when features are too closely related. And finally, be careful when you're looking at global or overall measures of feature importance, especially when your features are on totally different scales. Like if you have annual income, which could be anything from 0 to millions of dollars,
Mm.
and another feature that's always between 0 and 1, just looking at the raw impact might unfairly make the annual income feature look way more important simply because the numbers are bigger.
So it's like comparing apples and oranges, basically.
Exactly. In those situations, it's a good idea to either scale your features to a common range or use importance metrics that aren't as sensitive to those differences in scale.
Okay, so we've covered a lot on feature importance. Let's move on to our next XAI tool, partial dependence plots, or PDPs. What kind of insights do these give us?
PDPs are a way to visualize the relationship between a single feature and AI's prediction. But here's the key. They show you the average effect of that feature while averaging out the influence of all the other features. It's like isolating the impact of that one feature.
Okay, so instead of just knowing that, say, age is important in predicting someone's health risk, a PDP could show you how that risk changes at different ages. Like maybe it stays low until 50 and then starts to climb rapidly. That gives you a much richer understanding.
Exactly. And what's cool is they can reveal nonlinear relationships. Like with a simple linear model, you'd expect the effect of age to be a straight line risk going up steadily each year. But in the real world, things are usually more complex. PDPs can show you those curves and bumps.
Interesting. So what are some key things to look for when you're interpreting PDPs?
Well, first off, if you see a PDP that's basically flat, it means that feature probably doesn't have a strong effect on the prediction on average.
So, like, if you're building a credit scoring model and the PDP for middle name is just a flat line, it means middle names don't really matter. Maybe you could even drop that feature from the model.
Exactly. Another thing to watch out for, especially with categorical features, is if you see really high PDP values for a single category, that could be a sign of a problem.
Can you give us an example?
Sure, imagine you're predicting customer churn, and you have a feature called is deceased. If someone's dead, they're obviously not going to be a customer anymore. So you might see a huge spike in churn probability for the yes category in the PDP. But that could be a sign of data leakage, meaning the AI had access to information it wouldn't realistically have when making a prediction.
Right, like it's cheating a bit. So the AI might be super accurate in training, but in the real world, it would fail.
Exactly. And lastly, when your model is overfitting, basically, it's memorized the training data too well.
Yeah.
You might see some funky PDP results, especially if you have dominant categories. Like imagine you have a VIP customer category that's tiny but has unique behavior. Their impact might distort the PDP, so you might need to group categories to smooth things out.
Okay, that makes sense. So we've talked about feature importance to see which variables matter and PDPs to see how they impact the prediction. Now let's get to subpopulation analysis. What's the goal here?
Subpopulation analysis is all about checking how well the AI performs for different groups within your data. So instead of just looking at overall accuracy, you break things down by, say, age group, gender, income level, whatever makes sense for your problem.
So you're checking if the AI is working equally well for everyone or if it's worse for certain groups.
Exactly. Like if you have a fraud detection model and is much less accurate for people over 60, that could be a problem. Maybe the training data didn't have enough examples from that group.
Right. You don't want your AI to be biased against certain groups. And you also mentioned looking at the PDPs within these subpopulations. Why is that important?
Yeah, they can be really revealing. If a feature has a drastically different effect for one group compared to others, that could be a sign of bias too. Like if the predicted outcome jumps way up for people living in a certain region, it might be relying too heavily on that category for that specific group.
So spotting those differences is key. But once you find them, how do you actually fix them?
That's the tough part. One common culprit is imbalanced data, where some groups are underrepresented in the training data. Techniques like stratified keyfold cross-validation can help with that. It makes sure that when you split your data for training and testing, you keep the same proportions of each group.
So you're basically making sure the AI gets a good mix of examples from all the different groups.
Right. But sometimes balancing the data isn't enough. If you think the groups behave fundamentally differently, you might need separate AI models for each group.
Like going back to the age example, if the way younger users interact with the system is totally different from older users, it might be better to have two AIs, one tailored for each group.
Exactly. Sometimes a one-size-fits-all approach just doesn't cut it.
This has been a great deep dive into XAI. We've learned a lot from identifying important features to understanding their effects and analyzing performance across different groups. What's the main takeaway you want our listeners to remember?
I think the key message is that these XAI tools are super valuable for building trust in AI and making it more transparent. They can help us understand the why behind the prediction, which is crucial for responsible AI development.
So the next time you see an AI prediction and think, huh, why did it say that? You'll have the tools to investigate and explain the reasoning.
Absolutely. And this isn't just for AI experts. It's for anyone who uses AI or is affected by its decisions, which is basically everyone these days.
Right. On that note, we want to leave you with something to think about. How could you use these XAI techniques in your own work or life? What insights could you gain? It's all about moving beyond just accepting the output and starting to understand the why. Thanks for joining us for this deep dive into explainable AI.